Okay, so today our objective is to finish lecture set 3, which we will do. We're quite close to the end of that now. The only thing that we have left to do is cover the counting rules. We looked at an example of this last time very quickly right at the end of class. So I'm going to go over this example again. And this example is of our first counting rule, which is the basic counting rule. Once we finish lecture set 3, we're going to dive right into lecture set 4 and get as far as we can. Lecture set 4 is also a probability lecture set, or it's part of the probability unit, but it's focused on a very specific type of probability distribution. And it's quite a bit shorter. So there is a good chance that we'll be able to finish most of it today. And before we finish lecture, I will quickly go over what we have covered from assignment 2, which is due next Wednesday. But my hope is that by the end of the lecture today, we'll have pretty much everything you need to complete the assignment for part A. I think for part B, you've probably already covered all the material. So I'm a little bit behind where the lab is right now. But we'll, in the last like 2 or 3 minutes, well, maybe like last 5 minutes or so, I'm gonna go over what we have covered so that we're all on the same page in terms of what we can complete before Wednesday next week. Okay, so with that being said, we're gonna start off by reviewing the basic counting rule. The basic counting rule is the first counting rule that we discussed, and it's the first of 3. So we're gonna do basic counting, permutation rule, and the combination rule. The basic counting rule is the simplest rule. It effectively just says that for every action that is available to you in an experiment, for lack of a better word, the total possible number of outcomes is the product of all possible actions in that particular experiment. So for example, if you recall our work with rolling 2 die at the same time, if you consider each die or the roll of each die to be an action, then we have 2 actions in that particular experiment. If you consider that each die has 6 different outcomes associated with it, then the total number of actions in the sample space is going to be 6 times 6, which is 36. And if you think back to, actually I have the illustration here. If you think back to our illustrations of the sample space when we rolled 2 die, here's an example on slide 7, you can see that we have 36 different possible outcomes in this illustration. So we have 6 actions for die 1, 6 actions for die 2, 6 times 6 is 36, and we have 36 possible combinations of numbers that we can observe when we roll the 2 die. So our basic counting rule is effectively just a rule for enumerating the number of possibilities across all of the different actions that we can perform in an experiment. The value of the basic counting rule is it can help us enumerate the size of a sample space and help us to count how many possible ways there are to observe a particular outcome within the sample space that we are working with. Okay, so for example, the first illustration on slide 35 asks how many possible passwords are there if the first 4 entries have to be unique letters, and we can have either lower or uppercase, and the remaining 5 entries have to be unique numbers, and we can choose between 0 and 9. So basic counting says the total number of possibilities, or in this case, the total number of passwords, is going to be the product of the total number of actions available in each step, if you will. So here we effectively have 9 different actions. Okay, where each action is the total number, or each action is comprised of choosing 1 letter or number from all that are available to us. So the first action is choosing one letter from all possible lower or uppercase letters in our alphabet. So there's 26 letters. We're distinguishing between case. So that gives us 52 possibilities. So our first action has 52 different outcomes. Our second action is to choose another letter, lower or uppercase, that is unique to the first one. So we had 52 options in the first case, so we now have 51 options in the second case. In the third action, we have to choose one letter from all those that remain. We've already chosen 2 letters, so now we just have 50. And for the fourth action, same logic, so we now have 49. On action 5, we're starting by choosing one digit between 0 and 9. So the important thing here is that we're including 0 as its own number. So we now go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that gives us 10 possibilities for action 5. And then we decrease by 1 for each subsequent action because we have to choose unique letters and numbers. So the basic counting rule says multiply all possibilities for each action together. So we have 52 times 51 times 50 times 49 times 10 times 9 times 8 times 7 times 6. And that gives us 196,481,376,000. Okay. All right. So we will come to see in a little bit that this is actually also an application of what is called the permutation rule. And a lot of the time what we end up doing is combining the permutation and the combination rule with basic counting. And I'll show you an example of that in a little bit as well. Okay, the second example, how many 6-character passwords are possible if any letter and any number can be used in each space? So this is the same idea as the first example, except we now have no limitation on repetition. So if we could potentially randomly generate the password 111111, for example. So that means that in our 6 slots, so we can consider these to be the 6 actions. Okay. We have 26 letters, lower or uppercase, that give us 52 options for the first outcome. And we're also including the 10 numbers as possibilities in that outcome as well. So we now have 62 different possibilities in the first slot. In the second slot, we would have the same number of possibilities because there's no restriction on repetition. So that means that in each slot, we now have 62 different outcomes. So this is 62 to the 6, which is 56 billion 800,235,584. And in both cases, these would effectively be the sizes of the sample spaces that we're working with. And then from here, what we could do is use basic counting to try and enumerate different possibilities within the sample space so that we could work out probabilities. And that would be done in a very similar way, just depending on the restrictions that we place on the passwords. All right, the last example of basic counting utilizes or is based off of iPhone construction on, like, for example, the apple.ca website. Now, the options that you have when you're purchasing your iPhone have likely changed over time, but when I wrote the slide, these were what were available on the website. So when we build an iPhone, we can choose between 2 screen sizes, 5 different colors, and 2 different hard drive capacities. So how many different possible iPhones are there given these options? Same idea again. So we can think of each of these options as being an action. So we have screen size, coloring, capacity. We have 2 screen sizes, 5 colorings, 2 capacities. That gives us 20 different possibilities. Which in a way seems kind of low when you think about how many iPhones there are out there, but you know, it's obviously the case that there's a lot of people with the exact same phone. Okay, sorry, any questions about basic counting? In example 2, I use 62 because for each action, I can choose any letter, lower or uppercase, and any number between 0 and 9. So that's 52 possible letters plus 10 possible numbers for 62 total options. Does that make sense? Cool. Good one. Okay. The next definition is the definition of the factorial. The factorial is a definition that we require for the permutation and the combination rule. So both the permutation rule and the combination rule utilize factorial notation within them. Very simply, when we see a number with an exclamation mark beside it, that means a factorial. So it does not mean that the number is yelling at you. It means that we need to apply the factorial rule, which is you take the number and you multiply it by itself minus 1 times itself minus 2 times itself minus 3 all the way down to 1. Okay, so for example, 4 factorial is 4 times 3 times 2 times 1, which is 24. Okay, 20 factorial would be 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8. I think hopefully everyone gets it. 2 times 1, and that's going to be roughly 2.433 times 10 to the 18. And then the last one, which is 0 factorial, this is actually a rule that we use such that not every factorial is equal to 0. So you might say, okay, well, we stop at 1, like why don't we continue to multiply by 0? Because then in that case, everything would be 0. Well, you can think of it as you do multiply by 0, but 0 factorial in this case would be equal to 1. So in that way, you're not always ending up with 0 as the solution to the factorial problem. Yeah, actually, that explanation isn't the best. Let's just say we use 0 factorial. We define 0 factorial to be 1. That's the better way to explain it. And the factorial definition ends at 1. All right, so what can we do with factorials? Well, as I mentioned before, we use our factorial definition within the permutation rule and the combination rule. What a factorial actually does is tell us all the ways that we can order objects in a straight line. And in this situation, order does matter, so we can flip and alternate different units within that line. So for example, one of the ways that we can apply a factorial is to determine how many different ways 8 horses could cross a finish line. How many different ways 8 horses can cross a finish line in a race. Yes, Lorena, 1 factorial is 1. That's true. Is there a question? I hear typing. Okay, right, so we can use a factorial to determine how many ways we can order objects in a straight line. So if you think about horse racing, you have 8 horses running across the finish line. Assuming there's no ties, a factorial would count all the different arrangements of how those horses could cross the line. So the number of ways that 8 horses can cross a finish line is 8 factorial, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is going to be 40,320. Same thing with books on a shelf. How many ways can I arrange 5 different books on a shelf in my room or in my office or whatever? That would also be a factorial. 5 times 4 times 3 times 2 times 1, which I believe is 60. 20, no, 120. 5 times 4 is 20, times 3 is 60, times 2 is 120. Okay. Any questions? Okay, so now that we've defined the factorial, we can define the permutation rule. The permutation rule is effectively a rule that counts how many ways I can arrange R objects taken from M objects. So as we had just discussed, the factorial is telling us all the ways that we can arrange some number of units in a straight line. The permutation rule does the same thing, except that out of the total number of units, you're only collecting a subset. So you might say, for example, how many ways can I order 3 out of the 8 horses across the finish line? And that would be a permutation, 8p3. Or as you can see on the slide here, how many ways can I arrange 5 out of 10 books on a shelf? And that's a permutation, 10p5. Okay, so the permutation counts all the different arrangements of a subset of values, a subset of objects from a total number of objects in a straight line. And again, order matters. So we distinguish between like book A, book B, and book B, book A. Okay, so to illustrate the permutation rule, I'm going to start with a basic example of ordering 2 out of 4 letters. And I'm going to show you what the ordering would be so that you can see how the permutation is counting the different arrangements. So we have how many possible arrangements of size 2 are there from 4 letters, A, B, C, D? Okay, so we have M equals 4, R equals 2. We want to know how many ways can I arrange 2 out of the 4 letters. So this is a permutation, 4p2, which is 4 factorial over 4 minus 2 factorial. Okay, and this is equal to 4 factorial divided by 2 factorial, which is equal to 4 times 3 times 2 times 1 over 2 times 1, which is 12. Okay. Actually, just going to move this up. Okay, so what are these 12 different arrangements? So we're arranging 2 out of the 4 possible letters, and there's 12 different ways of doing this. So what does that actually look like? Okay, so here are the 12 arrangements. So we would have A, B, A, C, A, D, B, C, B, D, C, D. Okay, so that's 6. And now all we're doing is we're reversing the order of those 2 objects within the set. So for example, we would now have BA, CA, DA, CB, DB, and DC. So when we say order matters, this is what we mean. We mean that a set that contains the same units, but the units have been drawn in a different order, counts as a different set. So AB is different from BA when order matters. Okay, and the permutation is our way of counting arrangements when order matters. In the second example, it says, how many ways can one arrange 5 out of 10 books on a shelf? Okay, so here we would have 10p5, which is going to be 10 factorial over 10 minus 5 factorial. So this is going to be 10 factorial over 5 factorial. So this after cancellation is going to look like this. Okay, so then we have 90, 720, 720 times 7 is 4, carry the 1, 5020 times 6, 0, 2, 1, 1, 30,120, oh, 30,240. Right. No, so the question, are we expected to show all the arrangements? No, you're not expected to. I just wanted to explain what it means when order matters and why, what the 12 arrangements would look like. All right. Okay, so we're going to do a few more examples of the permutation rule, and then we'll look at a couple examples of the combination rule. The combination rule is the same idea as the permutation rule, except in that case, order doesn't matter. So with the combination rule, we're making an alteration to the permutation rule to not count any set with the same objects in it, regardless of order. So permutations, order matters. Combinations, order does not matter. Okay, how many arrangements of 5 cards are there in a standard deck of 52 cards? Excuse me. Okay, so this would be 52p5, 52 factorial over 52 minus 5 factorial, 52 factorial over 47 factorial, 52 times 51 times 50 times 49 times 48, which is 311,875,200. If selected from a population of size 5, how many permutations of samples of size 3 exist? Okay, so we have 5 units in our population, 1, 2, 3, 4, 5. I want to know how many permutations of 3 out of the 5 units. So this is going to be 5p3, which is 5 factorial over 5 minus 3 factorial, which is 5 factorial over 2 factorial, 5 times 4 times 3, which is 60. In a sporting league with 8 teams, how many arrangements of the top 3 teams are possible? Assuming no ties, of course. So we would have 8p3. This is 8 factorial over 8 minus 3 factorial. This is 8 factorial over 5 factorial, which is 8 times 7 times 6, which is going to be equal to 336. All right. Any questions? Oh. Okay, Dakota, do we need to show the cancellation? No, you don't have to. Like you can just show, you know, like you can write like 52p5 and then you can be like 52 factorial over 47 factorial and then give the answer. You don't need to write it out like I did. I just wanted everyone to see what's happening within the rule. Brooke, why did you stop multiplying the numbers How come you stopped at 6? Yeah, so the reason I stopped at 6 here, for example, was because when you work these two parts out, okay, so we have this thing on the top here, right? And then on the bottom, you're gonna have 5 times 4 times 3 times 2 times 1. So that means that this here cancels out with this here. So that's why I stopped at 6. And that's what happens in every factorial. So if you look at the other examples given above, you can basically see like whatever numbers on the bottom, I stopped one number before that in my way down. So like here I have a 2 on the bottom in the second example, so I stopped at 3. Here I had a 47 on the bottom in the first example, I stopped at 48. Just a cancellation. Any other questions? Okay, so the last rule is our combination rule. The combination rule is an adjustment to the permutation rule that removes any repeating sets. So for example, in the first illustration of the permutation rule, we arranged 2 out of 4 letters. We double counted, for example, the set AB and the set BA. So those are the same objects, but they're ordered differently, so they got counted separately. With the combination rule, we wouldn't do that. So combinations do not distinguish between the order of the objects. So this would be our rule for counting how many ways we can pull our objects out of M objects when the order does not matter. So we wouldn't distinguish between the set AB and the set BA when counting combinations. And this makes, yes, that's true. Yeah, so sorry, Mackenzie, a combination rule would be used for sample without replacement. Yeah, that's true. But that's true for the following reason. So a lot of the time when we're collecting samples, and a lot of the time when we're collecting samples, they're of objects that give us a measurement, like people would be a very good example. If you are collecting samples of people and you collect, say, person 1, person 2, person 3, and then you collect person 3, person 1, person 2, those are the same group of people, so you're getting the same information. So there's no reason to double count it. So the rationale for why we would use the combination rule in the illustration that you are asking about is because typically when we are sampling from a population of observations, we don't want to collect the same sample multiple times. We want different samples of people. So that's why the order doesn't matter in that case. Okay, so the combination rule, you can see, is actually very similar to the permutation rule. In fact, we can show, and I have this a little bit later, that the combination rule is actually just the permutation rule divided by r factorial. And you can see that here because we have m factorial over m minus r factorial. That is the permutation rule. So it's embedded within the combination rule. So it's simply just all the combination rule does is count the number of permutations and then remove any repetition. And that's done by dividing by r factorial. Okay, so for example, how many ways can 10 people, how many ways can 6 people be selected from 10 people to form a committee? And this would really be the same idea as to form a simple random sample. So we're building how many simple random samples of size 6 are we building from 10 people? So we would have 10C6, 10 factorial over 6 factorial, 10 minus 6 factorial. So this is 10 factorial over 6 factorial times 4 factorial. All right, so now what we can do is we can show that this cancels 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1, for example. All right, and that gives us 210. In the next example, we have how many ways can a committee of 4 people be chosen from 6 men and 4 women if there must be 2 men and 2 women on the committee? So this is an example of a combination of basic counting and the combination rule. So we essentially have 2 actions here. So choose 2 men from 6, choose 2 women from 4. Okay. So 2 actions, which are choose a number of men and choose a number of women. Each of these actions are a combination rule. So for the men, we're choosing 2 out of 6 men. So how many ways can I sample 2 out of the 6 men available? And for the women, it's the same idea. How many ways can I sample 2 out of the 4 women that are available to serve on the committee? Okay, so this here is going to be 6, choose 2, and this here is going to be 4, choose 2. Right? So that gives us 6 factorial, 2 factorial, 6 minus 2 factorial times 4 factorial, 2 factorial, 4 minus 2 factorial. That's 6 factorial over 2 factorial times 4 factorial times 4 factorial over 2 factorial times 2 factorial. Okay, and then that's going to give us 6 times 5 over 2 times 1 times 4 times 3 over 2 times 1. And that's going to give us 30 over 2, which is 15, times 12 over 2, which is 6, which is 90. Any questions? So the question is, in the first example, where does the 6 factorial go? So what I did here is I took the larger number and I canceled it with the numerator. So the 10 factorial over the 6 factorial gives me 10 times 9 times 8 times 7. So this thing reduces to 10 times 9 times 8 times 7 divided by the 4 factorial that's left over. Does that make sense? Okay, cool. Okay, so 2 more examples. In Lotto 649, 6 numbers are drawn from a drum with 49 different numbers in them. How many different winning lines are possible if order matters and if order doesn't matter? So the idea here is we want to know how many different ways can I pull 6 numbers out of 49 under the 2 different circumstances. So order mattering, order not mattering. So if order matters, okay, if order matters, then I have 49p6 different possible winning lines in the lottery. And this would basically be saying that the line 1, 2, 3, 4, 5, 6 is different from the line 1, 3, 2, 4, 5, 6, for example. So if you have the right numbers, but they're just rearranged, then that would not count as a win. So we have 49 factorial over 49 minus 6 factorial, which is 49 factorial over 43 factorial, which is something insane. I'm just going to move this over. Okay, so that's going to be 49 times 48 times 47 times 46 times 45 times 44, which is 10,068,347,520. All right, so if order mattered in the Lotto 649, this is how many different winning lines would be possible every time we played. Yeah, so Annalise, do you know if there is a way to do this easier in a calculator, or do you have to input everything individually? Scientific calculators typically have combination permutation rule built into it. Depending on the type of calculator you have, the way of accessing that will be different. On a basic science, like on a non-graphing calculator, it's usually something like second figure 5, second figure 6. On the graphing calculators, they're located in one of the menus. It's like a F3 menu or something like this, and you can select permutation combination. Basically, if you just look at your calculator and then you Google how do I do a permutation and then give the model number, you'll be able to find instructions for doing that. Okay, so the second example is when order doesn't matter. So here we would have 49C6. Okay, so this is going to be 49 factorial over 6 factorial, 49 minus 6 factorial. So that's 49 factorial over 6 factorial times 43 factorial. So this is going to be our solution to the first part, but divided by 6 factorial. So this is going to be the 10,068,347,520 divided by 6 times 5 times 4 times 3 times 2 times 1. And that's going to be 13,983,816. Okay. All right, so then the question is, if order doesn't matter, which is the way the Lotto 649 is actually played, what is the probability you win the grand prize if you buy a single line of numbers? Okay, so the probability of a win is going to be, in that case, since you only bought one line, 1 divided by 49 choose 6, which is 1 divided by 13,983,816. And then whatever that is, something very small. Something with 6 zeros, 7 zeros beside it, I would imagine. Let's see. Zero points. 1, 2, 3, 4, 5, 6, 7, 7, 1, 5. All right. So go out and buy your Lotto tickets today. All right, I think that, yes, that brings us to the end. Okay, does anyone have any questions about the counting rules? All right, so just a few quick conclusions and then we'll start lecture set number 4. So in terms of calculating probabilities of different events, everything boils back to the fundamental probability. So if you can determine the number of ways the event can occur and the size of the sample space, you can always work out the probability of an event. Okay, so the fundamental probability states that the probability of a particular event is little f over capital N. So if we can work out little f and capital N, we can always work out the probability that we're interested in. The conditional probability is a probability formula that tells us or is asking us to find the probability of an event in the space of another event. So it's saying given, or it's saying like this thing or action or outcome has to have happened. Okay, so we are restricting the size of the sample space to only the portion that is related to this particular outcome. What is the probability of observing a certain outcome within that restricted space? Mutually exclusive events have no intersection. So mutually exclusive events and independent events are never going to be the same thing because independence requires intersection. We use our permutation when order matters and we use our combination when order doesn't matter. So typically, for example, when we're sampling without replacement, we would be using combination rules. If you're sampling with replacement, that would be a basic counting problem. All right, so there's some exercises at the end of the lecture set as per usual, just to get additional practice with this stuff. And now we're gonna move on into lecture set number 4, which we need for the next assignment. Okay, lecture set number 4 is a shorter lecture set. It only has 2 topics, which are discrete random variable definition and some calculations associated with them. And then we discuss a special type of discrete random variable called a binomial random variable. Okay, so the first thing, what is a random variable? A random variable is a variable whose outcome depends on chance. So basically what I mean there is a discrete random variable is one that has a finite number of outcomes and associated with each outcome is a probability. The idea is we haven't observed the outcome yet, but we know that there is a probability of observing each of the different outcomes. So for example, if we consider all the people in this class, every single person in this class is likely going to have some number of siblings between 0 and say, maybe like 12 at the max would be my guess, but I could be wrong. And associated with each of those different outcomes is some probability. So maybe just hypothetically, let's say like 50% of the class has 2 siblings, 20% of the class has 1 sibling, 10% of the class has 0 siblings, and then the remaining percent have 3 or more siblings. So we don't know exactly, since if we draw a student randomly from the class, we don't know how many siblings that random student is going to have. But we could say the probability that this student has 0 siblings is 50%, or is whatever I said it was, like 10%. The probability that the student has 2 siblings is 50%, etc. So that outcome, the number of siblings associated with the student, is random until we actually pull the person out and ask them how many siblings they have. All right. So another example of this, oh, sorry, I'll show you another example in a second. When we're working with discrete random variables, we use a uppercase, lowercase lettering system to distinguish between whether it's observed or random. So when we use an uppercase letter, we're basically saying we haven't actually observed the outcome yet. So this random variable has the probabilities associated with it. When we use the lowercase letter, we're actually designating a value that is observed for the random variable. So we use capital X to represent the variable in its random state, and we would use little x to represent an actual value that has been observed for that variable. Right? With our random variable notation, we have what is called event notation, which is utilizes curly brackets, and we have the probability notation, which we had defined before. This isn't something that's crucial to what we're trying to accomplish in terms of the exercises on the assignment and whatnot, but it is technically how we would distinguish between an event and the probability of observing said event. So I'm going to show you some examples of how this would work so that you can see clearly what I mean by event notation and probability notation and how we would annotate a discrete random variable. Okay, so for example, every discrete random variable, capital X, has a probability distribution that's associated with it. The probability distribution represents the probability that X takes on each of its different possible outcomes. So for example, let capital X count the number of gears that are available within a certain set of cars. Okay, so there are 3 different possibilities for the number of gears that we might observe in a set of cars, and they are 3, 4, 5. The probability associated with picking a car that has 3 gears is 0.46875. The probability associated with picking a number of cars that has 4 gears is 0.375. And the probability associated with picking a number of cars with 5 gears is 0.15625, which gives us a total of 1, right? So our probability notation, an illustration of that is given in the second column. So here we can see the probability of capital X being equal to one of the possible outcomes within this particular experiment. So P of X equal to 3 is 0.46875. So that's telling us that there's a 46.875% chance that we pick a car from this particular population that has 3 gears in it. And again, in this case, our random variable, which is the number of gears in the car. So this is our random variable. These are the probabilities. The random variable is taking on a whole number discrete outcome. So the random variable is just an integer, like 1, 2, 3, 4, 5, 6, right? And this is always true for any discrete random variable. It has to be a fixed countable whole number. Next to the probability distribution, which is this table here. So this is our probability distribution. I have a probability histogram. The probability histogram is constructed in the exact same way as we would build a normal histogram. So the bar of each, or the bars of the probability histogram, they go to the associated probability, and each bar in the histogram is labeled with the associated number of gears, right? So we have 3, 4, 5. This bar is at 0.46875. This bar is at 0.375. And this bar is at 0.15625. Okay, so if we're asked to construct a probability distribution for a random variable, we're basically just being asked for what looks like a relative frequency distribution. And if we're asked to construct a probability histogram, we're basically just building a regular histogram, except that each bar represents one of the outcomes from the distribution. Okay, so for example, in question 1 here, I have a frequency distribution for the random variable x, which takes on values 1 to 4. So the first question that we're being asked is, what are the possible values for the random variable x? Okay, so from our distribution, we can see that x takes on values 1, 2, 3, and 4. Okay. So from the distribution, we can see x, 1, 2, 3, 4. We have the frequencies, and then we're being asked to express the possible values for x. So that's simply 1 to 4. That's all that that's looking for. In part B, it says, use proper notation to express the event that x equals 1. Okay, so event notation would just be x equals 1. Okay, so that's all that that's looking for. So when we're asked for event notation, this is what we were being asked for. Okay, in part C, it says, find the probability distribution for x given capital N is equal to 100. Okay, so a probability distribution is simply a relative frequency distribution. So we have x, 1, 2, 3, 4. Here we're going to have the probability for x. We are told that capital N is equal to 100. We have the frequencies for each outcome, 18, 15, 29, and then a missing frequency, which we'll talk about momentarily. So to find the probabilities, we simply take the frequency and divide by 100, because really what this is just a relative frequency distribution. So here we're going to have 0.18. Here we're going to have 0.5. Here we're going to have 0.29. Okay, and now what we have to do is figure out what C is. So we're told that capital N equals 100. So that means that 18 plus 50 plus 29 plus C is equal to 100. That means that, I think it's 97, right? 97 plus C equals 100. So C is equal to 3. All right, so therefore, the probability that x equals 4 is 0.03. Okay, in part D, it says, what is the probability we observe the event x equals 2? So this is P, x equals 2, that's 0.50. And then in part E, it says, what is the probability x is no more than 3? So the probability that x is no more than 3 is the probability x is less than, no more than. To me, that reads as x being less than or equal to 3, no more than 3. I guess the other, yeah, we'll do it like this. So no more than 3. So that's the probability x equals 1, 2, 3. So that's going to be the probability x equals 1 plus the probability x equals 2 plus the probability x equals 3. So that's going to be 0.97. Right. I know I'm going a bit fast, but this is all just kind of basic intro stuff, just pulling values out of the table. Does anyone have any questions? It says it in part C. Find the probability distribution for x given capital N equals 100. Sorry, Annalise, does that answer your question? The capital N is the size of the space. So it's telling us there is 100 possible units within the space. So 18 of the units are 1, 50 of the units are 2, 29 of the units are 3, C of the units are 4. So those total number of units have to equal to 100. Yeah, it's the size of the sample space. Yeah. Or just like the size of the sample. Yeah. Daniela, how would you find the value of X if not given? I don't understand the question. Yeah, so expected value is a different concept. I'm going to do that next. So that's a general formula across the whole space. I'll show you how that works in the next illustration. Yeah. Brooke, why did you make the frequencies into decimals? So in part C, we're asked to find the probability distribution for X. The probability distribution uses the relative frequencies. So a valid probability distribution would give the relative frequency or the percentage or the probability of each outcome. So that would have to be a number between 0 and 1 by definition. Cool. Okay. All right, so to follow up on one of the questions that was asked about expected value. Expected value is a concept or a definition that we apply to a discrete random variable. So the expected value of a discrete random variable is the same thing as the mean of that random variable. Now, this is a part in the lecture notes where students typically get very confused because we now have a different definition of mean. This is something that's going to happen on a few different occasions throughout the class. But what's important is that we distinguish between the kind of data that we are working with. So when we talk about the expected value of a discrete random variable, we are asking for the mean of a random variable that admits a probability distribution. When we talk about the mean, like add the numbers together and divide by n, that is referring to a mean for a sample collected where we have a quantitative number of observed outcomes. So we're not working with probabilities. The expected value is the mean for a variable that we technically haven't observed. We only have the probabilities of observing a different outcome. Right? To compute the expected value of a discrete random variable, we use the formula given here. Okay, so this means expected value. Associated with the expected value, as it's a mean, is also a variance or a standard deviation, which is given below here. Okay, and just like before, there's two different ways that we can compute the variance or the standard deviation of a discrete random variable. So we can use either what would be like a defining formula, or we can use what would be a computing formula. But the most important part here is that you are understanding the kind of data that you are working with. These formula only apply when we are working with discrete random variables. So these formula only apply when we're working with a variable that admits a probability distribution. So one like that shown on slide 6, for example. All right. The original formula that we had for mean and standard deviation, those formula apply when we are working with a sample that's been collected from some population. So they're a different kind of variable, so we have a different formula structure. All right, so I'm now going to show you an example of how these formula work. All right, so here is a discrete probability distribution. Okay, so we have capital X, which can be equal to 1, 2, 3, or 4. And we have the probabilities that are associated with each value of X. Okay, so this is a discrete probability distribution. Okay, and since we have a discrete probability distribution, that means that the associated probabilities, or since we have a discrete probability distribution, when we are asked to, for example, find the mean of X, that means use the formulas that we had defined on slide 8. So those formulas from slide 8 apply only in the case where we are working with a discrete probability distribution. All right, so in part A, it asks, what is the mean of X? So this is the same thing as the expected value. So here we would have mu X is equal to the expected value of X. So just, you don't have to write out both, but just for clarity, this is the same thing. Okay, so you can write E of X or you can write mu X. It doesn't matter, it's the same thing. The point is just to illustrate that they are the same. So you can, if you're asked for expected value or you're asked for the mean, that's asking for the exact same thing. Okay, so this is the sum over X of X times P of X. Or actually, I'll write this out properly. P of X. Okay, so all this is saying to us is multiply X times its probability and add that to the next X times its probability. So this formula is actually very easy to use. This is just saying take 1 times 0.18 plus 2 times 0.5 plus 3 times 0.29 plus 4 times 0.03. Right, and that gives us 2.17. And essentially what this is telling us is that we expect X to be equal to 2.17 on average. So it's saying, like, if we were to repeatedly draw observations out of this distribution over and over and over again, like some infinite number of times, the value is going to converge to about 2.17 on average. And I think I have a little bit of another, yeah, I'm going to come back to that in a moment. Okay, part B, what is the variance of X? Okay, so we have two different ways of computing variance, defining formula or computing formula. So the variance of X, if we use the defining formula, is the sum of X minus its mean squared times the probability of X. Okay, so this is going to be 1 minus 2.17 squared times 0.18. Plus 2 minus 2.17 squared times 0.50 plus 3 minus 2.17 squared times 0.29 plus 4 minus 2.17 squared times 0.03, which is equal to 0.561. Okay, and then this is the defining formula. We can also compute the variance of X using the computing formula. So in that case, we would have the sum over X, X squared times the probability X equals X minus mu X squared just like before, we don't have to do both. So you don't have to do the defining formula and the computing formula. They're just two ways of getting the same answer. So whichever one you prefer is fine. I just want to illustrate both so that you have an example of both. Okay. So here we're going to have 1 squared times 0.18 plus 2 squared times 0.5 plus 3 squared times 0.29 plus 4 squared times 0.03. Oh, and then minus 2.17 squared. Sorry, I'll just move this over. Okay, so working this out, we would end up with the same thing as before. Okay, the last question, part C, says, what is the standard deviation of x? So sigma x is going to just be the square root of sigma x squared. So that's going to be the square root of 0.5611, which is going to be 0.7491. Okay, here, I'm just going to zoom out so you can kind of see all of it. There you go. Okay, so those are examples of computing expected value and then computing variance and standard deviation. Again, to compute the variance, you can use defining formula or a computing formula. They give the same answer. It doesn't matter which one you use. It's just two ways of accomplishing the same goal. The standard deviation is defined in the same way that it was before. It's the square root of the variance. So once we have variance, we just take the square root and we end up with standard deviation. All right. Any questions on those computations? C is telling us the standard deviation of x. No problem. Any other questions? Okay. All right, so I'm going to talk a little bit about the interpretation of the mean. So the mean of a discrete random variable is what we expect to observe over many trials. This tends to confuse students because you see a value like 2.17 and you look at the distribution and you say, okay, well, there is no 2.17 here. But it is an average across all sampled values, which is why it tends to converge to a number with some decimal places associated with it. So we can think of the mean of a discrete random variable as being the average value after a large number of observations are drawn from the sample. In terms of application, when we see something with a positive expected value, that would mean that we are expecting a positive outcome. And the magnitude of that outcome would be used to determine the strength of the outcome, if you will. For example, on assignment number 2, there are 2 questions that are based on expected value, which are number 4 and number 5. In number 5, you're computing an expected value for each of the different friends, John, Sarah, and Chris. And, oh, actually, it doesn't ask you to compare them there. It's just a calculation. Yeah, so it doesn't, I guess it doesn't really matter then. But if you wanted to compare among the friends and say, which one do you expect to earn the most profit? That would be the person with the highest expected value. That's the idea. So we can use it as a tool for comparing what we expect to observe across different outcomes within the same space. So for example, on assignment number 2, in question 5, if we wanted to say something about, you know, which friend do we expect to earn the most money the next day, that would be the person with the highest expected value, for example. The other thing that I wanted to say about this is, in terms of visualizing or understanding the value, if you were to think about a like a scatter plot, something looks like this. Okay. So here we're going to have the value of X. So here we would have 1, 2, 3, 4. And here we would have, let's say, sample size, which is little n. So this is going to be the number of times that we've drawn out of the distribution. What's going to happen in the case, for example, in our previous illustration, is we're going to have something that looks like this. So it's going to start to bounce around at different values. And then over time, it would converge to 2.17. So it's, again, like what the expected value is telling us is where we expect the observed numbers to converge to as we repeatedly draw information out of the distribution. All right. Any questions? All right. Okay, so I'm not going to be able to get into the binomial stuff today, which is the last thing we need for assignment 5. So I'm going to stop here for material. So this is October 7th. Stop. And for assignment number 2, you are now able to do every question except number 6 from part A. Okay. And since we haven't done 6 from part A, we technically don't have the background for number 3 from part B. But my guess is that in lab, you would have covered the binomial material. So you technically could do 3 from part B, which leaves only question 6 from part A left. So you can do everything on assignment 2, except for question number 6 from part A. On Tuesday, we will cover the material for question 6 from part A, and this assignment isn't due until Wednesday at midnight. So that'll give you sufficient time to finish that question. It's actually a very short question. It won't take you very long to do it. We just need to learn about the binomial probability formula and what a binomial random variable is. Yeah, I can help with some questions at the end of class. But with that being said, I'm actually going to stop recording here for today. And I will be back to answer questions in a few minutes. I just need to run to the facilities. So